And now let's look at the squeeze theorem for sequences. And basically the squeeze theorem can also be adapted for sequences as follows. First, recall the general squeeze theorem for just general functions. Squeeze theorem: if f of x is less than or equal to g of x, which is less than or equal to h of x when x is near a, except possibly at a, and the limit of f of x as x approaches a is equal to the limit as x approaches a of h of x is equal to L. So if this limit is L, this is L, then this gets squeezed, and hence this becomes the limit as x approaches a of g of x is also equal to L. And basically an illustration of this is shown below here, just illustrated to recap on the squeeze theorem. So if this is x, this is y, and let's say we have, here is a, and let's say we have L, so this goes up across here, and L is right across there, like that. Yeah, to illustrate this, let's draw first h of x. Let's say it's the larger one, so it's always greater than g and f. So, but its limit is L, so this is the L, so it goes over to here. So let's say we have a function like this. This is h, and it goes across there, and it just goes around like this. This is h of x. And now let's say we have f of x. F of x is always less than h of x, or f of x. I mean g of x. So f of x is always less than h of x, or and h of x when x is near a. We'll just say it's less than for pretty much everywhere. Or actually, let's illustrate. It doesn't need to be less everywhere, just near a. So it's like that. And this is f of x, like that, like this. Alright, so if we have something like this where both the limits are L of f of x and h of x, then g of x, if it's always going to be less than, or in between h of x and f of x, near x equals a, let's say it's something like this. So even if it overlaps like this, as long as it's near, becomes like that, yeah. So if it's near it, it's going to be in between it. So in other words, this gets squeezed. So this one here, we could think of it as not near a. But anyways, so what we have here is, this is our f of x, and this gets squeezed inside, so thus the limit is also going to be, well, the same, L. So this gets squeezed inside, like that. Alright, so now, thus sequences we can, thus for sequences we can write the squeeze theorem as follows, and basically adapt the squeeze theorem to the sequences of theorem. So squeeze theorem for sequences, what we'll have is, if, so instead of the functions we have, if we have the sequence an is always less than or equal to bn, and this is where bn is less than or equal to cn, for we have n is greater than or equal to n0. Yeah, so for a specific point, if it's always going to be, if an is less than bn and less than cn, for a specific value here above this n integer. And we have, and the limit as n approaches infinity of an, if this equals to the limit as n approaches infinity of cn, which this equals to L, then by squeeze theorem the bn gets squeezed inside. So then the limit as n approaches infinity of bn, the in-between function, is also equal to L, and it gets squeezed. And then graphically we can see this as follows. Remember, it goes to infinity, so let's say we have the y-axis like that. This is the, make this a bit better straight, this goes to n like that, so that's n, and then let's say we have L across here, this is L, and let's say we have a point right here, this is n0, so to the right of this is n greater than or equal to n0. Alright, so first let's draw the larger sequence at Cn. So let's say we have Cn like this. So this is our Cn, and then it's going down and down, it has a limit of L. Let's just say it keeps going down, and we're just drawing integers now as opposed to a straight line or continuous lines as in the above theorem. So we have that. And now let's say we have the an, which is the smaller sequence. Let's say it goes something like this, and it's just the opposite of this one, and it goes in like that. I'll just write this down. So this one here is our AN, like that. So that's our AN. Actually, right outside of this interval, write this over here. So that's our AN. And now let's draw our BN, which is the middle one. So let's say greater than or equal to this one, and it has to be let's say it is greater than equal if for integer n is greater than or equal to n0. It's always in between there. So for example, let's say we have something like this. It goes like this, and then or actually, let's just say it comes out from here. Say it goes from here, and then past this one here. This is n0. Now, should I quickly move that around, just make it a bit more to the right here, so that we can draw one. Let's say it goes from here, then it goes above here, and then above this. Now it's always in between. Let's say it goes something like this, and then it goes all the way above here, and let's say it just keeps alternating, and so on. So you can see here, whether it alternates or not, as long because it's always less than it for n is greater than n0 or n0. Then notice how it gets squeezed inside. So we get over here, it gets squeezed. So we can write quote squeezed inside in between the two, larger and smaller sequences. And then this again is our Bn. Alright, so moving forward now, another useful fact about limits of sequences is given by the following theorem, which I prove at the end of this video in exercise 2. But let's look at this theorem. This is theorem 2. So if we have the limit as n approaches infinity of an, if this equals to 0, then the limit of the, that's absolute value. If we just remove the absolute value, it's also equal to 0. Because remember, absolute value, all it means is it doesn't matter if it's alternating or not. This one, it just means it's alternating, but it's still, or it can alternate, it's still going to go to 0. So then this is going to be an equals to 0.